All right, folks, so we are going to start this unit on limits by exploring some limits both numerically and graphing today. If I go too fast, just a reminder, you can always stop, pause, rewind, replay me, or shoot me an email with any questions. But I'm going to kind of zip right along with the idea that I can get you some time in class to start homework. So I'm going to go to page 3 of your new limits packet, where I'm going to do a little bit of review with respect to notation and how we communicate our knowledge about limits in writing, and then we're going to get down to business and actually get into the good stuff. So just a reminder with respect to notation, and that's really all I want to talk about on this page. Um, when we see the limit of some function as x approaches a value, that little minus in the superscript tells us that that is the limit as we approach that value from the left. Likewise, when we have the limit of some function f of x as x approaches a value with the little plus in the superscript, that plus tells us that our function is approaching that value from the right. The limit will only exist when the values from the left and right are equal. That is so, so, so important. Limit only exists when values from the left and right are equal. I really don't care so much about any of the information on that page. I really just wanted to hit that notation because that is going to be super important for us, not just today, but every day in this unit moving forward. All right, up at the top of page 4, we're going to start by talking using tables to find limits. And that's what this discussion is all going to be about here on page 4. On page 4 in example 1, they've given to us an equation f of x, which represents a parabola. F of x equals x squared plus 2. And we are going to examine the way this function behaves simply by looking at the values for this function in a table. So in order to be able to discuss this a little bit more quickly, the function has been put into the table. The values have been taken from that table and put here on your page. So what we're looking at in the first table is we've got some values for x. So in other words, we're looking at an x value of 0.9, then an x value of 0.99, an x value of 0.999, and lastly an x value of 0.99999. So notice that what's happening with these values as we move across the table is they're headed towards 1. The f of x values, just a reminder in your table, are going to be your y values. And in this particular instance, as we head towards 1, we're going from 2.81 to 2.98 to 2.99 to 2.999. The y values are headed towards 3. So in other words, is the x values are headed towards 1 from the left, because all of these values, if we were to plot them on a number line, are to the left of 1. Let's think about 1 being right here in the center. Here's 0.9, here's 0.99, here's 0.999. As we approach from the left, the y values are actually headed towards 3. So the limit as x approaches 1 from the left is going to be equal to 3. The way we would write this using limit notation is to say the limit of our function f of x as x approaches 1, and then to indicate from the left, I'm going to use that little minus superscript. That value is equal to 3. Likewise, for this same function, if we are now looking at x values, and again, if I'm to think about what this would look like on a number line, we've got 1.1, bunch of zeros, and 1's going to be this. I am now headed towards 1, but I'm headed there from the right side. So the limit of f of x approaches 1 from the right. We want to know now what's happening to the y values. The y values are going from 3.2 to 3.02 to 3.002. So the y values are headed towards 3, making that limit from the right also equal to 3. And expressed in limit notation, this would say the limit of our function f of x as x approaches 1. I use a little superscript plus to indicate from the right the y values are approaching 3. So now, because the limit from the left and the limit from the right are the same, we can say that the limit itself as x approaches 1 actually exists. So because the limit of our function as x approaches 1 from the left is equal to the limit of our function as x approaches 1 from the right, we are able to say the limit itself as x approaches 1 is also equal to 3. All right, it says let's graphically show this to verify our results. I say, how about let's not? I'm going to, again, in the interest of time, keep moving forward. In example 2, we've got a rational function, f of x equals x cubed minus 1 over x minus 1. And again, we want to start by looking at this numerically in a table. And again, our x values are going to be approaching 1. So this arrow indicates x values approaching 1 from the left. This table's set up a little bit differently than the first one. These x values are headed towards 1 from the right. But what we really want to look at is we want to look at the f of x values or the y values. As we head towards 1 from the left, our y values go from 2.7 to 2.97 to 2.99. These guys are headed towards 3. As we approach 1 from the right, going the farthest away, we're going from 3.3 to 3.03 to 3.003. These fellows too are headed towards 3. Note that even though at 1 the value of our function is undefined, we are still able to say that that limit exists because the value from the left and the value from the right are the same. So we can say the limit of our function f of x as the x values head towards 1, the y values head towards 3. Or in other words, the limit of f of x as x approaches 1 is equal to 3. Like with the first example, we're not going to graphically demonstrate. Number 3, I'm looking at the rational function f of x equals x minus 2 over x squared minus 4. And again, we've got a table here where our x values look like they're approaching 2 from the left. And our x values are headed towards 2, but from the right. And we want to look at this table and examine what's going on with the y values or the f of x values. Well, if I look from the left, I'm going from 0.25 to 0.2506 to 0.25006. So it looks like our y values are headed towards 0.25 or 1/4. Our y values go from 0.24 to 0.249 to 0.2499. So these guys are also headed to 0.25. So we say the limit as x approaches 2 because it's the same on both the left and the right. We can say the limit itself does exist and is equal to 0.25. The way we write this using limit notation is to say that the limit of our function f of x as the x values approach 2 is equal to 0.25. And again, I'm thinking about as the x values zero in on 2, the y values are zeroing in on 0.25. We want to now examine this and figure out what happens to our function as the value of x approaches -2. And that's what you see going on in this second table. So from the left, as we get closer and closer to an x value of -2, it looks like our y values aren't headed towards any one particular number, but rather they just continue to decrease. And as our x values approach -2 from the right, the y values here just continue to go up and up and up and up. So in this instance, we have two different limits. We've got the limit of our function as x approaches -2 from the left, which is equal to -infinity. And we've got the limit of our function f of x as x approaches -2 from the right, which is equal to +infinity. And because these left limits and right limits for -2 are two different numbers, we draw the conclusion that the limit of f of x as x approaches -2 does not exist, or DNE. So again, if the values of the left limit and the right limit are different, the limit itself does not exist. All right, so that's kind of the first topic for today, or the first goal, or the first objective, is to look at those limits numerically as to what they look like in a table. I'm going to say page 5 is your homework. The conclusion over here is going to be, what do the limits look like? So limits are going to go in that box where it talks about your conclusion. Left limit, right limit, and general limit. In the meantime, I'm going to boogie over to page 6 and we're going to talk about looking at limits graphically. This is exactly the same idea as limits were in a table, but instead of looking at the values in a table, we are now going to look at the values on a graph. So it says answer all questions based on the graph for each function. For the first one, I'm going to put a couple arrows here. So this should have an arrow. This should have an arrow nosediving. And again, when we talk limits, what we're really looking for is we're looking for y values. As the x values head towards a particular number, what's happening to the y values? So for instance, in number 1, when we're looking for the limit of f of x as x approaches 0 from the right, what that really means is that as the graph heads toward 0 from the right, what's happening to the y values? So this is where, when I have a graph, I think about this as just hopping on the function and taking a ride. Since I'm starting to the right, I'm going to hop on that function somewhere to the right of 0. I'm going to ride toward 0, and I want to know what's happening to the y values. Well, as I head toward 0 from the right side, the y values are headed down, 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 or towards -infinity. To determine the limit of our function as x approaches 0 from the left, I'm going to head on or hop on that function to the left of 0, and it can really be anywhere to the left of 0, and I'm just going to head towards 0. And as I approach an x value of 0, it looks like my y values also head towards 0, making the limit of our function as x approaches 0 from the left equal to 0. Now, because our left limit and right limit for 0 are different, that means the limit itself as our function approaches 0 is a DNE. And again, I'm really looking at these two to see if they're a match, if they're the same. If they are, that would be my limit. Because they're not, the limit does not exist. In the fourth line, it says f of 0 equals. So in other words, remember this is the same as f of x. They're saying when our x value is equal to 0, what is our y value? So again, that's what that's talking about. When x equals 0, y equals what? Well, the point 0, 0 is a point on my graph. So when I have an input of 0, my output or my y value is also 0, making f of 0 equal to 0. We've already talked about end behavior with respect to limits, so this is nothing new. As x goes to infinity would represent the right end of the graph. So as our x values become more and more positive, well, as I head towards the right end of the graph, it looks like the y values are headed towards that horizontal asymptote, making the right end behavior 3. And remember that x values of negative infinity represent the left end, or the left side of the graph. And if I look at the left end of the graph, that graph is headed down, 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 or negative infinity. All right, I think I'm going to look at number 2. We'll do one more together. I'll give you a few to do on your own, which you can check, and then we are going to be done. Number 2, I'm going to zip through these a little bit quicker because as we do them, we should get better and better and more proficient. In number 2, we're looking at our function as the x values approach 1 from the right. So I'm going to hop on my function to the right of 1. It can be anywhere to the right of 1. And I'm going to head towards 1. And it looks like as I head towards 1 from the right, my y values head towards 2. So the limit of f of x as x approaches 1 from the right is 2. Number 2, limit of f of x as x approaches 1 from the left. Well, in order to find this, I'm going to hop on the function somewhere to the left of 1. I'm going to ride that function towards 1 and as my x values head towards 1, my y values head towards 3. Notice that I don't care whether that's an open circle or a closed circle. It's just whatever y values our function is getting close to. Because our limits from the left and right are different, that means the limit as our function approaches 1 does not exist. The value of f of 1 will be the closed circle at x equals 1. So an input of 1 will generate an output of 2, making the value of f of 1 equal to 2. Infinity is the right end of my graph, so my right end of my graph is headed towards that vertical asymptote at y equals 3. The left end of my behavior, well, notice that my graph never does go to negative infinity. It looks like the furthest to the left my graph goes is somewhere between -2 and -3. And because my graph doesn't go to negative infinity, its limit does not exist. All right, what I'm actually going to have you do is pause at this point. Go ahead, find the limits for graphs 3, 4, and 5. And then once you have found those, you can go ahead and unpause the video and check your answers. All right, welcome back. For number 3, I had those values, -2, 3, a DNE. 3, infinity, infinity. Hopefully yours match up with mine. If they don't, I would suggest checking with someone that sits near you and see if you can get an explanation, or you can always email me. Up at the top for number 4, I had a bunch of infinities. I had a DNE, a 0 and a negative infinity. And again, I would encourage you to check with each other, and you can always reach out to me by email. And lastly, for number 5, see how your answers match up with mine. And again, please reach out and ask questions if you don't understand how or why those are what they are. All right, folks, so this wraps this one up. As far as homework is concerned, you've got those tables on page 5 to look at, and you've got page 7, which are some more limits defined graphically. You've also got that review for cumulative exam number 3 that you can and should be starting to work on, because we all know that's going to creep up on us a lot faster than we think it is. All right, take care till we see each other face to face. I hope you're well. Can't wait to see you. Bye for now.